Okay, so you know how we always get into some really interesting stuff here on the deep dive, right? But this time, it feels especially fundamental.
Oh, yeah.
You sent over this article about an experiment that they're proposing at Caltech to try to detect quantum fluctuations in the fabric of space itself.
Right.
Like, wow.
Yeah, it's pretty ambitious.
Yeah.
It gets right to the core of this huge problem in physics, which is, how do we put together our understanding of the quantum world,
Yeah.
all the tiny stuff,
Yeah.
with Einstein's theory of gravity, which, describes the universe at the largest scale.
Right. Yeah. It's like the very small and the very large.
Exactly. And we're talking about like the very nature of reality here.
Okay, so that's a pretty big statement right there. Can we break that down a little bit? Because I think for a lot of people, quantum fluctuations in space, it's still kind of an abstract concept.
Sure.
What's the problem that they're actually trying to solve with this experiment?
Okay.
And I guess our mission in this deep dive is to really get into like, what is this experiment? How's it designed? And why could it be so groundbreaking?
Okay, so the central issue is this incompatibility between Einstein's theory of general relativity and quantum mechanics.
Right.
So general relativity, it describes space-time as smooth and continuous.
Okay.
It bends and curves in response to mass and energy, and that curvature is what we experience as gravity.
Right.
Quantum mechanics, on the other hand, tells us that at the smallest scales, the universe is governed by probability and uncertainty.
Okay.
And everything is quantized. It comes in discrete packets.
So it's either kind of like a smooth flowing river or it's like a collection of tiny little energetic grains.
Exactly.
It's hard to see how those two things go together.
It is, and physicists have been looking for this unifying theory, this quantum gravity that could kind of bridge this gap for decades.
Right.
And one of the key predictions of many of these quantum gravity theories is that even seemingly empty space isn't actually perfectly still.
Mm.
There should be these quantum fluctuations, these tiny fleeting disturbances at the smallest possible scales.
Okay, so we're saying space-time is always kind of jittering at this quantum level. How could you even begin to try to detect something like that?
Right.
I mean, that seems impossibly small.
Yeah, it's incredibly subtle.
Mm-hmm.
But that's where this experiment at Caltech comes in.
Okay.
They've come up with a clever approach, and it actually builds on the technology that allowed us to detect gravitational waves in the first place.
Oh, really?
Yeah, remember LIGO, those massive instruments that were designed to pick up ripples in space-time from black hole collisions and things like that?
Huge, huge cosmic scale waves.
Exactly. So
Yeah.
think of something similar, but much smaller and tuned to detect vibrations at a totally different frequency.
Okay, so how does that relate to these quantum fluctuations?
Okay, so the fundamental principle is the same. Using lasers and mirrors to make super precise measurements of distance.
Okay.
So they're proposing to use a pair of interferometers that are positioned very close to each other, about 5 meters in length each.
5 meters. So still pretty big, but not LIGO scale.
Right, exactly. And what's really fascinating is the frequency range they're targeting, which is tens of megahertz.
Right.
That's much higher than LIGO's operating range of a few hundred hertz.
Right.
And it's because it's in this high-frequency range where these theoretical quantum fluctuations of space-time are predicted to occur.
Okay, so you've got these two devices sitting next to each other. They're firing lasers. How do they actually see these fluctuations?
Okay, so within each interferometer, a laser beam is split, and it's sent down 2 perpendicular arms.
Okay.
Bounces off mirrors at the ends, and then the beams are recombined.
Okay.
Now, the lengths of these arms are super carefully adjusted so that when the light waves recombine, they undergo destructive interference.
Destructive interference. Okay.
Think of 2 waves on the surface of water.
Mm-hmm.
If they meet just the right way,
Yeah.
a crest meeting a trough, they can cancel each other out, resulting in a flat surface.
Oh, okay.
It's similar to what happens with laser beams. They're made to cancel each other out, ideally resulting in a completely dark output port, so no light should emerge.
A completely dark output.
Yeah.
That sounds really hard to do.
It's a huge technical challenge, but here's where it gets really interesting. The idea is that if space-time itself is fluctuating at the quantum level,
Okay.
these tiny rapid changes in the fabric of space might just slightly change the path lengths of the laser beams in each arm,
Right.
just enough to mess up that perfect cancellation.
Okay.
And this could allow single photons to sneak through that normally dark output port.
So you're looking for a single photon, basically.
Potentially, yeah.
At that dark core could be evidence of
Yeah,
these quantum fluctuations.
exactly.
That sounds incredibly delicate.
It is incredibly delicate, which is why a single detection wouldn't be enough to claim a discovery.
Right.
There are other potential sources of noise, tiny vibrations, thermal effects, even stray light
Sure.
that could cause photons to appear at the output. So this is where having the second interferometer becomes crucial.
Ah, so this is where the second one comes in, right? So you're doing this two-pronged approach to tackle this problem of noise. How does this second one help distinguish a real signal?
The key insight is that genuine quantum fluctuations in space-time should be correlated between the two interferometers because they're both experiencing the same underlying fluctuations in their shared region of space.
Right, because they're right next to each other.
Exactly. Whereas instrumental noise is likely to be uncorrelated. Random jiggles in one detector shouldn't directly cause jiggles in the other.
Got it. Okay, so you're looking for these correlated blips in both detectors at the same time.
Exactly. You're trying to filter out the random background noise and isolate a genuine signal.
So this isn't the first time that physicists have tried to find these fluctuations, right? There have been other attempts before. What did they try and what have we learned?
You're absolutely right. This is a long-standing quest in physics.
Yeah.
One approach involved looking at the light coming from very distant stars. And they were looking for any signs of blurring or kind of rapid twinkling that might be caused by quantum fluctuations in space, distorting the light's path over those huge distances.
Okay, so like looking for the effect of those fluctuations on light that's traveled a really long way.
Exactly. And another significant project was the holometer at Fermilab,
Okay.
which used large-scale interferometers in a different configuration to search for what's been called holographic noise in spacetime.
Okay. And what did they find?
So far, none of these experiments have found definitive proof of these fluctuations.
Okay, so still looking.
Yeah.
Now, the article mentioned a potential problem with something called Lorentz invariance.
Right.
What is that, and why could it be a problem for this experiment, or the theories behind it?
Okay, so Lorentz invariance is this fundamental principle in physics
Okay.
that basically says the laws of physics should be the same for all observers, regardless of how they're moving at a constant speed relative to one another.
Right.
Imagine throwing a ball. Lorentz invariance basically says the laws that govern that throw should be the same, whether you're standing still or moving on a spaceship at a constant speed.
Right. Okay, so the laws of physics don't change just because you're moving.
Right, exactly.
Hmm.
But some theories that predict these quantum fluctuations in space-time suggest that those fluctuations could lead to very subtle violations of Lorentz invariance,
Oh.
meaning the way light or particles behave might depend on how fast the observer is moving.
Okay.
And we've never seen that before.
Yeah.
The issue is we've done tons of really precise experiments,
Yeah.
and they haven't found any evidence of these violations, which puts really tight constraints on how big these effects could possibly be.
Right. So any theory that predicts these fluctuations, it can't contradict what we already know.
Exactly. It's a balancing act.
Right.
So it's not just about building a sensitive detector. The theory has to work with everything else we know about physics.
Okay. Makes sense. Now, the article talked about this idea of entropic gravity and pixelons as the theoretical basis for all of this. Can we unpack those ideas a little bit?
Yeah, so the framework behind this proposal is pretty innovative.
Okay.
It's based on this idea of entropic gravity, which is a pretty radical perspective.
Okay.
So instead of thinking about gravity as a fundamental force like electromagnetism, it suggests that gravity might actually come from more fundamental principles related to information.
Information?
Yeah, specifically the entanglement entropy of quantum systems.
Okay, hold on. I'm trying to wrap my head around this.
Yeah.
So what we think of as gravity might just be the universe processing information.
It's mind-bending, right?
Yeah.
And so within this framework of entropic gravity, the Caltech team is using this concept of a pixelon field
Okay.
to try to model these fluctuations in space-time.
What is a pixelon field?
Okay, so imagine a digital image.
Yeah.
Up close, it looks smooth, but if you zoom in far enough, you see it's made up of individual pixels.
Pixels, right?
Yeah. So the pixelon field is this theoretical idea that space-time itself might be similar.
Okay. So space-time has pixels.
In a way, yeah, at an incredibly tiny scale,
Okay.
made up of these fundamental pixels that can fluctuate.
Mm.
And the behavior of these pixelons could give rise to the fluctuations that the experiment is hoping to detect.
So they're modeling space-time as kind of grainy, and those grains are interacting to create what we experience as gravity?
Exactly.
Okay, so the narrator in the article did have some doubts, right? Particularly about this idea of entropic gravity and how it relates to Lorentz invariance. What was the concern there?
Right, so the skepticism comes from the fact that if this theory predicts fluctuations that violate Lorentz invariance, even in very tiny ways, it could lead to things that we should have already seen
Hmm.
in those very precise experiments that have tested Lorentz symmetry.
Right, because we've already done those experiments.
Exactly. And the narrator's pointing out that if these violations were big enough to be detected by this new experiment, it's kind of surprising we haven't seen them already.
Right, it's another balancing act.
It is.
You've got to fit this new theory in with all the stuff we already know. So let's just say for a moment that they are successful, they managed to detect these quantum fluctuations. What would that mean for our understanding of the universe? Why is this such a big deal?
Well, a successful experiment would be huge. It would be a revolution in physics.
Right.
It would give us the first direct experimental evidence for the quantum nature of space-time,
Mm.
which is a key prediction of many theories of quantum gravity.
Right.
This would be a big step towards finally unifying quantum mechanics and Einstein's theory of gravity,
Yeah.
giving us a much more complete and fundamental understanding of how the universe works.
Right down to the smallest level.
Exactly. It could completely change how we understand cosmology,
Mhm.
the behavior of black holes,
Why?
even the nature of reality itself.
That's a lot to take in. It sounds like the physics community is watching this experiment with both excitement and, a little bit of healthy skepticism,
Absolutely.
which is probably appropriate.
Yeah, the potential reward is massive, but the challenges are huge too. I mean, that's what happens when you try to push the boundaries of knowledge.
So if someone listening wants to learn more about the basics behind all this, the article mentioned brilliant.org
Yeah.
and their interactive science courses, specifically a course on quantum mechanics. Why is it so important to understand quantum mechanics to really grasp what's going on here?
Quantum mechanics is fundamental to this whole thing.
Okay.
The experiment is based on core quantum principles, like wave interference, that cancellation effect we talked about,
Right.
the probabilistic nature of photons, and maybe even more complicated things like quantum entanglement,
Okay.
if the models of the pixelon field are right.
So you really need to have that background to understand the implications.
Exactly.
Okay, so to recap, we've got this Caltech experiment that's trying to detect these super subtle quantum fluctuations in space-time
Right.
using these two tiny interferometers, looking for single photons that might leak through because of these fluctuations.
Yeah.
And that second interferometer is there to help filter out the noise. The theoretical ideas behind it are pretty out there.
Definitely.
This entropic gravity
Uh-huh.
and a pixelated model of space-time. But there's still a lot of challenges, particularly making sure these new ideas don't clash with what we already know from experiments like with Lorentz invariance.
Absolutely.
But if they do manage to pull this off, the payoff is huge.
Huge, yeah.
It could change how we understand the universe on a fundamental level.
You've summed it up perfectly.
It really makes you wonder, what if all that empty space out there isn't really empty? What if it's this sea of quantum activity at a scale that we can't even really fathom?
Right.
How would that change how we think about reality itself?
That's a big question.
It is, but this experiment might help us answer it, even if it's a long shot.
I think so.
It's definitely worth watching.
I agree.
That's all the time we have for today. Thanks for joining us on the Deep Dive.
Thanks for having me.